We'll start the session. So we are talking about normalization over here. So like in the previous session we discussed, uh, we have this thing in second normal form. So again, for the third normal form to get the data into third normal form, what we need to have a basic condition is that data should be in at least second normal form. So first normal form, second normal form should have been complete. Only then we can work on the third normal form. So in third normal form, a new thing that comes into picture is the transitive dependence. Transitive dependence is something like I mentioned over here in this table, we have system use and hourly rate. So hourly rate is dependent on the system used. So I cannot say that roll number is the only primary key that can identify name, system use and hourly rate. But because hourly rate depends on system used. So in that case, this shows us clearly, if you see this picture, from roll number, I can identify name, I can identify system used, I can identify the hourly rate for a particular system used, but there's another dependency on the hourly rate. Hourly rate is completely dependent on the kind of system being used. When the attributes are not free from each other, there is no dependence within the attributes. That means the attributes are transitively dependent on each other. You understand my point? So, the solution to the above anomaly is provided by the third normal form, which deals with the problem of transitive dependence. When the attributes in a particular table identify other attributes besides the primary key, that is called transitive dependence. This part over here, where system used an hourly rate, if you see over here, this part, sorry, the system used and hourly rate, these are transitively dependent on each other. So system used and hourly rate. For every hourly rate, I have to look at the system. If I have to update a system, or if I have to update the hourly rate, let's say I need to enter another system which is quad core processor or Pentium quad core Intel i5 processor or i7 processor with an hourly rate of, let's say, 50 rupees per hour. Then it is dependent on the system. It is not dependent on the roll number directly. That shows that there is a transitive dependence between hourly rate and system used. Hourly rate is dependent on system used. To to solve this anomaly, to solve this thing and get the data into third normal form, what we do is the conditions like I had mentioned earlier. The relationship is already in second normal form. No non-prime attribute is transitively dependent on the key. So this should be removed over here for the data to be in the third normal form. I know my data is in second normal form, but this thing, the transitive dependence, this should be removed. To remove the transitive dependence, what we do is, so A is dependent on B, B is dependent on C, but B and A are also dependent on each other. So like that way, we cut the relationship and create two tables. So let's say this is roll number, this is system used, and C is the hourly rate. So what we do is we create a table having A and B, and then we have B and C. So system used and hourly rate will create a separate table for us, and roll number and system used would be in a separate table. Like over here, I'll show you. Yeah. So we would have student system as a table. So what we are doing actually is, hold on a second. Yeah. So in this table, what we are doing is we are actually keeping these three in one table, and we are creating a new table for these two, system used and hourly rate. So I'll have two tables from this, and overall three. So I will be having 1, 2, 3, and 4 tables for my data to be completely normalized into third normal form. One would be the hours assigned, another would be the course table. So this is my first table, this is my second table. So roll number, student name, and the system use, this would be my second table, sorry, third table. And this would be my fourth table, where would have system use and hourly rate. So just a single thing that we need to remember, that there should not be any transitive dependence. So like over here, I have roll number, name and system used. I have system used and hourly rate. These were in a single table. Both of these were in one table. Now we have separated them into two separate tables, so that if I need to update any hourly rate, I just update it over here rather than updating it in this entire table all over again. So in order to avoid this thing, we do this way. In order to avoid this thing, we keep on making our data much more easier and simpler, so that any kind of anomalies, any kind of redundancy, where the data is redundancy is where I have duplicate data, where I have duplicate information. So to remove that duplicacy, remove that redundancy in my database, I keep on decomposing my tables into smaller forms. So first we started with the functional dependency, then we understood what is fully functional dependency, then we started decomposing that. First we started filling the table with all the missing values. That was the first normal form. Then in second normal form, we decompose the table based on the key attributes. So we separate the table on the basis of key attributes. Then in the third normal form, we find out that is there any transitive dependence in each of the tables that we have got in the second normal form. Over here, let me get back to you again. So after second normal form, we had these three tables. Now in every table, we check it out. Is there any insertion, updation or deletion anomaly? Like in this table, the student system charge table, we have that insertion, updation, deletion anomaly, because hourly rate and system used are dependent on each other, which is called the transitive dependence. That's why we separated these tables into two different tables with system used in both the cases. So over here, system used in this charges table, system used is my primary key. Over here in this table, roll number becomes my primary key, roll number. Over here, course code is my primary key. Again over here, course code and roll number form my primary key. In that way, this is how my data is into third normal form. It is a complete normalization as of now. Now, still, there could be certain anomalies as well. This is an exercise. I'll leave it to you later on. So there is another thing which is called BCNF. It is Boyce Code Normal Form. So we call it as this thing. Over here it is mentioned Boyce Code Normal Form. The only difference between the Boyce Code Normal Form is Boyce Code is simply, BCNF is simply a stronger definition of 3NF. It is again, it's a third normal form only, but it is a better version of third normal form, what you can say. So BCNF makes no explicit references to first and second normal form as such, nor the concept of full and transitive dependence. It doesn't have it doesn't need that the data should be in first or the second normal form, and not it wants that the data should have the concept of full and the transitive dependence. Now BCNF states that if and only if every determinant is a candidate key. Here determinant is a simple attribute or composite key on which some other attribute is fully functional dependent. Like, where's my example? Like over here, course code and roll number, that's a composite key. So every course, C100 is a unique over here, C200 is a unique key over here, unique unique combination of two attributes that helps to determine the total hours used by a particular system used by a particular student in a particular course. So it tells us, helps to determine the total number of hours used by a student in a particular course. So the combination of course code and roll number is unique in this table. Now that's what they are saying in BCNF. If and only if every determinant is a candidate key. So determinant is something that helps to determine a value or another attribute. So over here, course code and roll number helps you to determine total hours. So course code and roll number is a determinant and total hours is a determined. So now again we go back to the definition. It says that determinant is a simple attribute or a composite key on which some other attributes is fully functional dependent. Now, for example, let's say we have a table, this one, it is referring to this table. We have serial number, city, status, product number and quantity. This is a suppliers table. So they have put it into first normal form by filling in all the empty values, all these empty values, S1 Amritsar 20, they have just filled in. They have just filled in, nothing else. And we have another table which is a manufacturer's table, which has ID number, which is the manufacturer ID, the name of the manufacturer, the item number that the manufacturer is producing or manufacturing, and the quantity that item is being produced into. So we have serial number, what we have, serial number, city, status, product number and quantity. Now, serial number and product number helps to identify the quantity. How? Let's say serial number 1 and product number P1. This is a unique combination, whereas S1 Amritsar, S2 Amritsar or S1 and status 20 is repeating continuously. But serial number and P1, I have S1 P1, I have S2 P2, I have S1 P3, I have S1 P4, S1 P5, S1 P6. Now S2 P1, it's not S1 P1. So that is a unique combination. So if I need to identify that how much quantity of product P1 has been produced, has been supplied or has been generated. So serial number and P number helps me identify the quantity. That's what shows that it's a functional dependence between serial number and product number. Now serial number and product number is a composite determinant, but serial number also helps to determine the supplier name as well. Where it is? I guess a table is missing over here, a column is missing. So there should be a column over here mentioned as supplier name, S name. So over here, let's say there is another column, S name. That's a very old presentation, guys, that I'm showing you. It's from my engineering time. So I'm using the same thing. So there is another column, say S name. So now from a serial number, from a supplier number rather, this is a supplier number. Every supplier number would have a supplier name. Let's say I have a supplier, say ABC Corp, I have DEF, I have Krishna suppliers, I have Duroflex, I have Novartis, whatever it is. So we have supplier names over here as such. So, but for S1, the supplier name would be same as ABC. This is just an example that I am giving you. Don't think that S1 has different supplier names. Every supplier name would have a single supplier. Every supplier number would have a single supplier name. You can't have different supplier, same supplier number as, let's say, S1, and there are different same like A, B, C, D, E, F, G, E, H, 4 different suppliers under supplier number 1. So that's why I say, that's why it is mentioned over here that a combination of supplier number and product number helps you identify a quantity, and supplier number also helps you to identify supplier name. Here supplier number is simple attribute determinant. So in both the cases I have supplier number, which is a common determinant for S name, for serial name, supplier name, and for quantity I have supplier number, which is constant. This is not changing at all. So it is a simple attribute determinant. Now again, coming back to our case where we have course student system charge, which are not in 3NF, are also not in Boyce code normal form. The course student course has course code, roll number, name, system use, hourly rate, and total hours. It's coming back to the original table what we had earlier before the third normal form. Yeah. So we have course code, course name. Sorry, let me check what all columns it is mentioning. Okay. We have course code, roll number, name, student, system used, hourly rate, and total hours. So it is. We have course code, course name, roll number, name, system use, hourly rates, and total hours, not the teacher name. So let's say this is the one. This is the table that we have after the second normal form, what it is referring to. Course code, roll number, name, system use, hourly rate, and total hours. What it has to say. Let's go through it. So it says that here course code and roll number determines total hours. Yes, on that basis we have created this table as well. Now roll number helps to determine the name, system use, and hourly rates. Yes, here roll number is the common determinant but not the candidate key. So the relation course code student is not in BCNF. For a data to be in BCNF, it should have a common value that acts as a determinant. It should not be a candidate key. If it's a candidate key, it cannot be, or a candidate key or a composite key, it cannot be in BCNF form, Boyce code normal form. So that's not something that you should bother about. BCNF is not used, rather, yeah. So now the fourth normal form, it says that your relationship should be in third normal form if it contains no multi-value dependency. What is multi-value dependency? We have covered functional dependency, we have covered fully functional dependency, we covered just now transitional dependency. Now it comes to multi-value dependency. So let's say we have a table that has customer name and address. So Raj, he stays in Delhi. Another Raj stays in Amritsar. Suneet stays in Amritsar. Another Suneet stays in some Batala. And Ankit stays in another place. Now, multi-value dependency occurs when two or more independent valued facts about the same attribute occur within the same table. How? So Raj stays in Delhi and Raj stays in Amritsar as well. So that's a multi-value dependency. I have multiple values for a particular single attribute in a given table. It means that what I'm reading over here is, it means that if in a relation R having A, B, and C as attributes, B and C are multi-value facts about A. Over here, this is A, this is B. So there are multi-value facts in B for A. I have New Delhi, I have Amritsar. Again for this guy Suneet, he's staying in Amritsar, he's staying in Batala. That's a problem. A guy cannot be staying at two places at the same time. So, which represents that A has multi-value dependence on B and A has multi-value dependence on C. This is example where we have three attributes. I am giving you this thing only which says that A has multi-value dependency on B because there are multiple values in B for a single value of A. That shows multi-value dependency. First, in order for a table to contain multi-value dependency, it must have three or more attributes. Okay. Secondly, it is possible to have a table containing two or more attributes which are interdependent multi-valued facts about another attribute. What does this mean? It means that it is possible that a table has two or more attributes. It can have two also, which are interdependent multi-valued facts about another attribute. We'll see it in an example over here. Like, so physics. We have physics Rahat mechanics. We have physics Rahat optics. We have physics Ankit studying mechanics. We have physics Ankit with course book of optics. Now again, chemistry Ankit. These are again, so Course help you determine the textbook, right? And course has dependent on student as well. So course has a multi-value dependency on student because for every course there are multiple students. For every course there are multiple textbooks. You won't read a single textbook for thermodynamics, for physics. There are different topics in physics. You have different subjects in computer science. For computer science course, you will have software engineering, you have SQL, you'll have Python, you have C, you have C++. So there are different textbooks for every course. So different textbooks for every course and different students, many students studying the same course. Fine. That's what. Physics is studied by Rahat, physics is studied by Ankit, physics is studied by again Rahat. So there are multiple values for physics to identify a student. So course has multi-value dependency on a student. Course has multi-value dependency on a textbook. So we have, though this indicates that we already have a multi-value dependency. How to handle this? Rule to transform a relation into fourth normal form. A relation R having A, B, C as attributes can be non-loss decomposed into two projections. So we can divide this table into two parts. One is course and student name, one is course and textbook. That's it. Again it is saying like, let's say this is A, this is B, and this is C. So we can have A and B, a table saying A and B, and we can have a table saying A and C. So these are values over here, it has values over here. So that way we can create our table into fourth normal form, and if only if there is a multi-value dependency of attribute on B and C. There is the only one condition. If a table has multi-value dependency, then only we can apply a fourth normal form. And whenever there is a multi-value dependency, you just split the table into those number of new tables. So the number of multi-value dependencies you have, you will create those many tables. So over here we'll have a table saying course and student name and course and textbook, like this. We have course and student name, we have course and textbook. So over here we don't have repeated values saying physics Rahat, physics Rahat, physics Ankit, physics Ankit, physics Ankit. We have just one single combination for physics Rahat, for physics Ankit, for chemistry Ankit, for English and Raj. There is no repetition of physics Rahat or physics Ankit ever in this table. Now, same. Physics course books, we have these course books, mechanics and optics. In chemistry, we have organic chemistry and inorganic chemistry as textbooks. In English, we have English literature and English grammar. That's how we put our data into fourth normal form. So this was the example. Let's say we have this example, Suneet, with working on equipments like a PC and a workstation. He has a desktop and he has another workstation. He's working in two languages, English and German. So what we'll do is we'll first fill this table to put it into first normal form. We'll put Suneet PC, Suneet P workstation, Suneet workstation to fill in all these places. So we have Raj, we have three languages, English, German, Spanish. So we filled all these things, right? First we flattened the table to put it into first normal form, what we studied earlier. Now for a fifth normal form is something that is not so far used as of till date. It is not used. It is a concept that is brought into industry but not used widely at all till date. So I'll give you again just a brief of it. It says that the data should be in the fourth normal form. It cannot be further non-loss decomposed. There we cannot divide the data further. That indicates that my data is already in the fifth normal form. So fifth normal form is a little practical use of a database designer, but it is of interest from a theoretical point of view. That's why I said that it is not something which is practically used. It is a theoretical point of view, and a discussion of it is included here to complete the picture. Leave it. In all of the other further normal forms discussed so far, no loss decomposition was achieved. So there is, if I divide this table further, there won't be any loss of data to me. You understand my point? Let's say I create tables saying physics and Rahat, separate table for physics, separate table for chemistry, separate table for English. I won't lose anything. I can give it, I can create tables like this, let's say. Sorry. So let's say I create tables over here for, I have course and name. So only physics, Rahat, physics, Ankit. I create another course table for chemistry. Chemistry, let's say Raj is studying chemistry. Let's say chemistry, Sheldon is studying chemistry. Let's say I have another table, English. So Raj is studying again English. We have English. Avan is studying English. So I have three tables over here. This one, and this one. From which table? From this table, the course table. The course student table. I have divided this table based on the courses into three different tables. Let's say this is physics course, this is chemistry course, and this is English course table. Now at any point of time, do we feel that there is any loss of data? No, because whatever is present over here, it is present in all these three tables. So when this table cannot be further decomposed into smaller sets, that means my data is into fifth normal form. That is the highest normal form that we have. So they are giving just the same example that I gave you. So let's say they divided Suneet and ABC and Suneet and product name. So Suneet and product name, sorry, agent and company, agent and product name. Now the redundancy has been eliminated, but the information about which companies make which product and which of these products they supply to which agents has been lost. Like, so what my table says is, let's understand this table. So agent is Suneet. He is working with ABC company and CDE company, and he's selling the products nuts, screws, and bolts. What Raj is doing is he's just selling the bolts. Over here, I know that Suneet is working with ABC and CDE, and Raj is working with ABC company. Suneet is selling nuts, bolts, screws. Raj is selling bolts. But so the redundancy has been removed. I have only there is no repeated value in this combination. The redundancy is something where the values are repeated, but the information about which companies make which product. Now over here I get to know from this table that company ABC manufactures nuts, screws, and bolts, this part, and CDE sells only bolts. But when I have this table, these are two separate tables. My information that which company is selling which product is lost over here. So the natural join of these projections over the agent column is putting all together these things like Suneet ABC, Suneet ABC, Suneet ABC, nut, bolt, and screw. Suneet with CDE, nut, bolt, and screw, because ABC manufactures nut, bolt, and screw, and CDE manufactures only bolt. So Raj with ABC bolt. I'm confused over, yeah. So again I'll explain you again just listen to me again. So ABC company sells nuts, screws, and bolts. CDE sells only bolts. So what they did is, as Suneet is associated with ABC and CDE both, so he would be selling all the products, nuts, screws, and bolts, right? That's what they have mentioned. ABC nut, ABC bolt, ABC screw, CDE nut, CDE bolt, CDE screw. But I don't know why it is, because CDE just sells bolt, let me just read this out again. The redundancy has been eliminated, but the information about which companies make which products and which of these products they supply to which agents have been lost. The natural join of these projections over agent column is okay. Now, if I put a join on these tables, P1 and P2, if I put a join on these tables on column agent, you understand my point? If I put a inner join on these tables on the column agent, it will pick up Suneet nut, Suneet bolt, Suneet screw. Whereas CDE company just sells bolts, not nuts and screws. So, if I am joining these two tables, are you getting my point? Guys, these are two tables that we have got from this thing based on their multi-value dependency. Now, I have these two tables. Let me say I put a join on these two tables. So,
Sir, what is gold star?
I'll let you know that. Just ignore the star part. मैं आ रहा हूँ उस पे. I'm coming to that part. Hold on. So, when I do this thing, when I put a join on table P1 and P2, when I put a join on these two tables P1 and P2, this statement select star from P1 inner join P2 on P1 dot agent is equal to P2 dot agent. This is the common column in between these two. So what it will do is it will pick up Suneet ABC nut, Suneet ABC bolt, Suneet ABC screw, Suneet CDE nut, Suneet CDE bolt, Suneet CDE screw. See, Suneet CDE nut, Suneet CDE bolt, Suneet CDE screw, Raj ABC bolt. That's it. Only one. Because there is only one matching record over here. So this is what an inner join will do to this table. But we are sure about this thing that ABC company manufactures just nut, screw and bolt, and CD manufactures bolt. But over here, if you see over here, CD is manufacturing nut, bolt and screw all, which is not the right case. You understand? So over here, uh, my separation of tables is not working good for me. There is loss of information, or rather, there is wrong information that I am getting from this table after putting a join on these two tables. So they have put a bolt, they have put a star over these three things because these three are the major things that they're manufacturing: nut, bolt, and screw. So just a highlight that these are the major three things that we are manufacturing. The companies are manufacturing. It's not something to be highlighted about. It's just a thing to explain. It's not technical. It's just a way to explain things that these are the three major topics, the products that we are talking about: nut, bolt, and screw. So, the main idea behind me explaining you this thing is that when we put a join on these two tables, there is loss of information or an information that is wrong. So, what we do is we select the company, we divide this again further, we create another table mentioning that company is company and product. So ABC manufactures nut, bolt and screw, and CD manufactures bolt. Now when we'll combine it with the company part, Suneet ABC, this table, same table, I'm picking up this same table. So Suneet ABC nut, Suneet ABC bolt, Suneet ABC screw, Suneet CD nut, Suneet CD bolt, Suneet CD screw. This is after the join that we put. But now when I say Suneet ABC nut, Suneet ABC bolt, Suneet ABC screw, Raj ABC bolt and Suneet CD bolt, this is something that helps me identify. Now I have these four tables with me. table P1, table P2 and table P3. So again, let me come back to you again on this front. I have this one. So I have this table. I have these tables. So over here, when you see, now if I'll put a join, if I need to know that which product is manufactured by which company, so this table P3 can be joined with this table P1. You understand my point? If I write another query, let's say I write another query. So select star from P3 inner join with P1 on P1 dot company is equal to P3 dot company. This will give me this table, agent, company and product name. I will get this table. So when I run this query, select star P3 inner join P1 on company between this agent and company table and the product table, I'll get this table. So which says that Suneet ABC. So nut, bolt and screw. Suneet ABC, nut, bolt and screw. Suneet CD, bolt. Suneet CD, bolt. Raj ABC. Raj ABC, bolt. Raj ABC bolt over here because it is bolt over here. So again it would be another join over here, not just this much. Inner join with another table which is P2 on P3 dot product name is equal to P2 dot product name. This is getting messier and messier. Let me just put this thing a little here. So when we have these three tables, we need to put a join to understand that which person is working with which company and manufacturing which product. So the join statement would work like this: P3 with P1, P3 with P2. With P1 it will work on company, with P2 it will be joined on the product name. So when I say product name, P3 product name on P2, so nut, it matches with nut and picks up the agent name. Then it checks the company P1 table and checks that ABC company, so it gives ABC nut. It picks up bolt, it checks out Suneet over here, checks out CDE company, so it says Suneet CDE bolt. It picks up screw, says Suneet, it goes over here, it sees that Suneet is with ABC, it picks up Suneet as screw. Raj with bolt, so Raj has bolt, but he works with company ABC. Suneet manufactures, sells bolt, but he's working with CDE for bolts. So that's how कहाँ चला गया मैं? Yeah. So So over here, but consider the different case. If the agent is an agent for a company and the company makes a product, then he always sells that product for the company. Obviously, the person is working with a company and a company makes a particular product, but every agent is specific to selling a particular product or a particular set of products. So the same thing what we studied over here, this is the same table. If you see this right left hand side where my cursor is, slide number 198, we have agent, company and product name. Here also we have agent, company. This is the same table that they have picked it up. This is the same table that they have picked it up in the next slide. The same one. This is the same one. So P1, P2, P3 are the three tables. All redundancy has been removed in all the three tables. There are no repeated values in any of these tables, no repeated set of values or a combination of values in these tables. If we put a natural join or inner join on P1 and P2 is taken, the result is, if we put a join, inner join with P3 on P1 and P2, we'll get this table. Sorry, if we put a natural join between P1 and P2, we'll get this table where we don't know which company is it, and CD doesn't manufacture nuts, it just manufactures bolts. But if we do what do you say, a join with the P3 table, then this is the final result which gives us the clear picture. So in fifth normal form, the crux of fifth normal form is when you divide the table into multiple tables based on the multi-value dependency, making sure that there is no repeated values, no set of values that are repeating, removing, which is called, we remove the redundancy, right? But there is no loss of information because we can any day join these tables to get the information which is the total information that we require. That is the fifth normal form. Again, fifth normal form is a very theoretical concept. It is not something which is used in databases till date, but if required, it is something that can be used. It is not that we use regularly or on daily basis. So on this note, we complete the entire normalization. Only 5 minutes of time is left with the session. I would like to explain you what indexing is. If you have any doubts on normalization, please let me know.